Swayam Prabha. Digital India. Educated India.
We have been talking about instruction set architecture, and last class we saw about addressing modes, different varieties of addressing modes. So we will just see one more addressing mode and then see two very important classes of instructions that are in modern processors and their needs. Okay. Okay. So we'll take two very important classes of instructions in addition to one more additional addressing mode. I hope you have started writing the assembly programs. You have written a couple of assembly programs. If it is no, please make it yes by writing it today. Okay. So let us see some instructions like, okay, now you see this simple program. This is how you write the assembly code, and you would have seen such instructions. Now you see that there is a jump from this instruction to this label and another jump, right. Now how will this instruction be decoded? So there is an assembly equivalent of this. How will it be assembled? So I am sure all of you know that from IIT Madras. Let us say there is some code for jump 1 greater than or equal to, let me say it is 0x8 something, and normal jump, say this is 0x4, this is the opcode, and what will be stored after that opcode? So what is stored here is basically the offset from this. Suppose this instruction is stored at 1000, this is 1004, let just assume 1008, this is 1016. Actually you go and store 16 here, right. So essentially it means that if this jump is this condition is successful, the jump will happen, and what you need to do is from the current program counter or from the address of the current instruction, which is 1000, add 16. So this will basically take you to, and this is what you will load, this will be the address of the next instruction that you are going to execute. So if you just store 16, if this instruction is stored at A, then what will be loaded again for the next instruction will be fetched from A plus 16, which will be this, correct. So this is actually called as program counter relative addressing. PC relative addressing. So normally program counter will always point to the next instruction, right. So you may store here 12. So it will, after this is fetched, your A will be pointing to this, plus 12 will be this. So depending upon the architecture, you can the compiler or the assembler will do that, and what you are storing here is the offset, right. So offset relative to the program counter, right. So what is the advantage of doing this? I can load the program anywhere, okay. It is not, so if L1, I need not fix L1. So this is another one more manifestation of the segmentation in some sense. Okay. So, so in this two instructions we have introduced here, the jump and what you call as JCC, jump on conditions. So JGE, JL, we have seen lot more this. So these are called, just to recap, these are called conditional branches. This is unconditional branch. Okay, fair enough. Okay, so this is another one more addressing mode, and that is favorable in two ways for us to actually, the compiler cannot compile unless we have PC relative addressing. So the architecture has to support PC relative addressing for the compiler to compile it properly. Otherwise, if there is no PC relative addressing, please note that the compiler cannot compile a code at all, cannot model the jump, because while it is compiling it will not know where this L1 will be actually loaded in the memory, right. So this is mandatory, this is the most important thing for that, right. Any doubts? Yes.
What if L1 was the command JGE?
Then it will be a negative value, minus 16.
But it will go to the negative side, right?
No, it will not, no. Suppose your L1, sorry, L11, okay, L11 was here and this was 990, whatever, 996, okay, 996, 994, then you will put, so 1004 minus 10, so I will put minus 10 here, because your PC will be 1004 after 1000 is fetched, so minus 10, so I will put minus 10. So it is PC minus 10, not just minus 10, right. So whatever is stored in the PC, that is added with the number that is on the offset. So if that number is a negative number, then you go back, it's backward jump, otherwise you do a forward jump. Got it? So then we will now go into two important instructions that form, it's mandatory in the modern instruction set architecture, and these are all demanded by the operating system. Okay, those two classes of instructions are atomic instructions and predicated instructions. So the x86 also has these atomic instructions and predicated instructions. What do you mean by atomic? In general, where you say this is an atomic unit? Basic, now what do you mean by basic? Indivisible. Okay. Okay, we can't split it up into smaller parts, right? So you should now say, no, atom contains electron, proton, neutron, no, neutronic unit or protonic unit or whatever, electronic unit, but it is not divisible anymore. Okay. Now, why do we need such type of instruction? What do you mean by an indivisible instruction? What do you mean by an instruction that cannot be split? Right? These are all questions that need to be answered. Okay. Now, let us take one interesting problem that you will encounter in operating system, left and right. Whatever you touch in operating system, close your eyes and touch, you will have this problem. Okay. And that problem is called producer consumer problem. What is a producer consumer problem, right? So when will there be any conflict at all, any problem at all in world? I am asking a philosophical question. When there will be a conflict? I walk east, you walk north, south, or you walk west. Will there be a conflict? No. So when will there be a conflict? When will there be an accident? When will there be an argument? When will there be, see, let us take everything. When will there be a misunderstanding? Okay, so if we share a resource, okay, right, if there is relative grading, there will be more conflict than absolute grading, right, correct? Right? So when we share a resource, there will be conflict, right, and that is what, and the whole operating system, when you study operating system in the next semester, you will see that everywhere there is some entity sharing a resource with some other entity, right. So broadly, if you look at operating system, there will be some part which will be managing the memory, there will be some part which will be managing the CPU, there will be some part which will be managing the devices, some part which will be managing the files, okay. So file management, process management, memory management, IO management, all these things are there, and every fellow will be touching every other fellow. So take any two random entities, X in some management and Y in another management, somewhere they will share some resource, and that makes the entire operating system complex. So when two fellows share the resource, right, there should be some consistent way in which they share, correct, right. If that consistency is not maintained, then the resource becomes absurd, correct. So the way by which we will enforce that consistency is by a process called synchronization. Okay. Now I will take the simplest of the examples that you will further learn there in your operating system course. Probably you will spend 2 weeks learning this alone, and I will give you an example of two fellows trying to share a resource, and what do you mean by a consistency policy there, and what it means to enforce that policy. Okay. I will give you an example where two fellows are sharing a resource, and we will define what I mean by consistency, and then we will see how to implement that consistency. Are you getting this? Three important things. So one of the important problems that you face when you operate with a system is that there is a keyboard, there is a processor. Keyboard is some million times faster than the processor, slower than the processor. Then you have a disk which is say not million times, but considerably slower than the processor. Then the RAM, which is faster than the disk but slower than the processor. So you have varieties of devices working, and they are interacting together with each other by actually exchanging information, right. So when there is a fast entity and a slow entity, both of them transferring data between each other, the only way to see that there is no data loss is by having a shared buffer. So there should be a shared buffer to which the producer will be the consumer will be consuming from this shared buffer, and the producer will be producing into this shared buffer. If there is a speed mismatch, wherever there is a speed mismatch in computer systems, immediately you will see a buffer, right. When you see the file systems, you will learn in great detail in your operating system course, there will be something called a buffer cache. The buffer cache is basically responsible for storing some data from the disk. When data is transferred from the disk and consumed by the CPU, it lies in one cache called a buffer cache. Similarly, when you type on a keyboard, you will see this gets stored in a keyboard buffer, and the process consumes it from the buffer, right. When you transfer things over the network, again network will be slower than this, so then there is a buffer, right. So everywhere there is a speed mismatch between device A and device B, there is a shared buffer. Now let us look at the simplest version of this problem, where there is one consumer consuming into this buffer, another consumer one producer producing into this buffer, and one consumer consuming away from this buffer. Okay. Now are you able to understand? So this is one process. Process means what? a program in execution. Okay, Palghat, just note hello world.c is a C program. When you compile it, a.out is the executable program. When I press ./a.out in your shell, right, then it becomes an executable program in execution, right, a program in execution, then it becomes a process. Okay. So, a process is always a program in execution. Please remember this for eternity. Very good. Now, okay, now there is a producer process, there is a consumer process. Now, let us try and make a consistency here. What is the rule of consistency? I am always selecting green. Okay. Can you guess what could be the rules for consistency here? Simple rules. I am putting something in, I am taking something out. What is consistency?
No loss.
Okay, it is the same order, but these are two different processes, not the same processes, enqueuing and dequeuing. Assume this buffer is a queue, but what is consistency then? When will I go? What is consistency generally? Something which should stop me from doing something wrong, right? That is what we call by consistency in this context. So, what are the wrong things? Taking, exactly, beautiful, okay, excellent. So, consumer should not consume from an empty buffer. This is rule A. Then the next rule, somebody other than her. Producer should not produce into a full buffer. Correct? So, these two are the consistency policies. Okay. Now, we will write a program, right? We will write a program to basically ensure, right, that this consistency is maintained. Are you all able to follow? Very simple things. Okay. Now, let us go to the, let us write a program for this. Okay. Now, who is good? Who is? You seem to be a little radioactive today. So, can you just, Kavya, can you tell me the program? Can you dictate? Anybody else? So, what should be the producer program and what should be the consumer program? The producer should know it is full, consumer should know it is empty. So, how will I know it? So, let us know that this is, there are n, the buffer is of size n. Okay, n is size of buffer. Now, what should the producer and consumer? Producer should, so producer produce, first step is produce an item. Then he is going to go somewhere and say put the item in, let me call that buffer as B, put the item in B. Okay. So, at this point he needs to do some action, check what? Check for buffer full. So, we can say if buffer not full, put the item in B, and this he will be repeating, the producer will be doing for his lifetime while 1. Okay. Similarly, consumer what he will do? While 1, if buffer not empty, remove item from B, consume, remove item I from B, consume I. Okay. So, this is basically what the producer and consumer will do, and they will keep on doing it. So, there will be a producer, that is a while loop, infinite loop. What will the infinite loop do? The producer will keep on producing item, and then the next step, if buffer not full, he will go and put the item. If buffer is full, what he will do? He has to wait, right? If buffer not full, else he will be repeating this second statement itself. Okay, else repeat to, again he will go and see, check. Again here else repeat. Okay. So he will be checking it again. So this is basically the producer consumer problem. Now how will I check buffer is not full, or how will the consumer say buffer is not empty? What is the easiest way of doing it? Maintain a count of how many elements are there. Okay. So I will have a shared variable, this is where the problem comes, because I have a shared variable called count which was initialized to 0 when these programs. So both these producer and consumer will share this. So what the program now becomes a slightly, when count less than n, put the item in B, and I will put count equal to count plus 1. Okay. And similarly, I will put here when count greater than 0, remove item I from B, so here count equal to count minus 1. Okay. So there is a count equal to count plus 1, and there is a count equal to count minus 1. So this will be inside a bracket. Correct. So now this thing works perfect. Count less than n means buffer is not full, count greater than 0 means buffer is not empty. And whenever I remove an item, I decrement count, whenever I add an item, I increment count. Okay. Right. But now count is a shared variable. It is shared by the producer process and the consumer process. The same count here is incremented, it is decremented. Got this? Now let us go to the next and see. Suppose I want to do count equal to count plus 1 and count equal to count minus 1. Let us take these two programs. Count is in memory. Let us say it is in some 1000. This is where so 1000 is address of count. Okay. Now what I will do, I will say move EAX comma 1000, increment EAX, move 1000 comma EX. So let me say this is I11, I12, I13. What I will do here, I21 is move EAX comma 1000, decrement Okay. So, are you able to follow these two programs? Okay. Now, what will happen is, as we had seen in the lab class, when multiple processes are executing, there is no guarantee that all these three instructions will be executed together. What could happen is, when I11 finished and it was about to execute I12, the operating system may decide that okay, enough for this process, let some other process start. So, there could be a context switch which we had been talking of to this fellow. Okay. And now I can finish this entire thing and then I will come back and start executing I12. Correct? So, let me say count is say 5. I am producing and consuming. So, that after this action both production and consuming, the value of count should remain at 5, right, it should remain at 5. That means when this executes once and this executes one, count is count plus 1 and again it becomes count minus 1, or count is count minus 1 and then count plus 1. So, it should remain at 5. Now, let us see what is going to happen. So, 5. Now, what will happen here, first I11 executes, it makes EAX is equal to 5, correct. So, let us say I start here, then there was a context switch, then I21 starts executing, again it will also make EAX is equal to 5, but this EAX is different from this EAX because there is a context switch. The same register is used, but the content of these registers are stored and the content of those registers are open. Okay. When I move from one context to the next context, right. So, EAX is 5, this again EAX will be 5. Now, I22 EAX will be decremented, so EAX becomes 4, then I23 what happens? The content of 1000 actually becomes 4, then there is a context switch here. Then I12 executes, it will increment EAX, but that EAX in this context is 5, so EAX becomes 6 and I13 now becomes, so 1000 actually gets the value 6, then both completes. So, at the end of this action of one production and one consumption, the value of the value of count will be 6 rather than 5. The same thing I could demonstrate wherein I21 executes, then there is a context switch and then I12 I13 executes, then again it goes back to I22 I23. So, in that context what would have happened? First I21, so EAX will be 5, then I11 EAX will again be 5, I12 EAX will be 6, I13 1000 will be 6, and then I go back here, I22 EAX will be 4 for this context, and then I23 1000 will be 4. So, I can get a value 4 also for this. Okay. Are you able to follow? Right? Yes. Huh? Context switch is, I am executing, I am a different process, you are a different process. When I am executing, I will have some memory allocated for me, I will have some values in my registers. When I am moved out, all those values need to be saved, so that when I restart, I should start from exactly where I left, okay, right. So, they are executing in order, but between them they can go and do ping pong any time. That is what I explained you in the, did you attend the lab class? Yes. So, what did I tell you in the lab class? You have millions of fellows logging into Gmail server, so I will give you some time, I will pull you out. Unfortunately for me, you are the red process and I pulled you exactly after you finished that move, and then gave it to Raghav, he starts executing that 3, and then the control comes back to you, and when it comes back, what is the value of EAX you will have? You will have as 6. right? You will have as 5 and then you do the increment and then you store. Right?
But the count is independent to each of it.
Count is a shared variable dependent on both of them. I am using the same count. Count is represented by 1000. Did you start writing assembly programs? Then you should not ask this question. Okay. Right? So 1000 is the address where count is stored.
The DS will be different, right?
DS and no, that's what. If I have a shared variable, I should have one segment which is focusing on the shared variable which is shared by both. Correct? So ES, FS, GS, one of them I can use for storing that 1000. Okay. I could even have the same DS for both. Nobody stops you. It is just a selector that I need to put, right? So I can put 2 for this, 2 for this. But in essence, I could have some other segment which is sharing this. So I can say move ES colon 1000 and here also say some ES colon 1000. Here also ES colon 1000. 1 minute. Okay. So I could have one extra segment dedicated for sharing these. If you go back to the assembly language model. Okay. Understood? Yes. Understood? Increment can happen on a register. I think it can happen on M8, M16, M32.
First process it was 5. When we went to next process, it became 4.
No, it doesn't become. It also came as 5. Then here, no. See, look at. It also started as 5. Then it became 4. Then you went and stored 4 into 1000.
So when we go back to the first process,
The its EAX is different, right? The context. That's what. Your EAX, you both of you use the same hardware resource, but when you are using, your value will be there. When you are moved out, this value will be stored in your process control block. Next time you come, again it will come back. So this is a problem. So I have a shared variable. One fellow tries to increment it, one fellow tries to decrement it, and then if both of them messes up, then you land up with an inconsistent value. Correct? So what should you do here? Either when I start incrementing, nobody else should do anything. Right? It can also, so here we have only 2 processes. When I start incrementing, the consumer should not touch that variable. When he starts decrementing, I should not touch that variable. So somehow I have to put a guard, right? I have to put a guard so that only one fellow can touch it. Okay, so let us go back to our other example and I see, now let us use this. I put a guard here. Right? I put a guard here and that guard should basically give me this concept. So we need some, and who, see, the architecture should enable you with some instruction which can help you implement this guard. Okay. Because this part, this count equal to count plus 1 and count equal to count minus 1 are very critical. If I go and start executing both together, then we will land up with problem. So this is, so with respect to producer and with respect to consumer, there are 2 critical sections. One for each, right? Such that when one process is executing its critical section, the other process should not execute its critical section. Are you able to understand? When one process is executing the critical section, the other process should not execute its critical section. Right? So there should be somebody who is ensuring this. So please understand, critical section is that there are 2 processes, each one of it has its own critical section. Why we call it critical? Because if both of them execute the critical section at the same time, then there could be some mix, so that the whole consistency may go to toss. Okay. What would have happened in the previous, the example that we saw just before? I will still have 5 elements in my buffer because I have produced one thing, I have consumed off. but the count will be either showing 6 or the count will be either showing 4. What is the consistent state? Count should be equal to exactly the number of elements that is there in the buffer, but we may get some wrong numbers there, correct. So, in this case there are two fellows each having its own critical section, and they should share the it is called the critical section because when producer is executing its critical section, if the consumer also starts executing its critical section, both are different, right. Count equal to count plus 1 is the critical section of producer, count equal to count minus 1 is the critical section of consumer. When this fellow is executing this, other fellow tries to execute, then there is a problem, there is a scope for a problem. So, somehow when producer is in its critical section, I should stop the consumer from going into the critical section. For that, there is an instruction called test and set of some variable v. V is a bit. Okay. In addition to count, I will also share a variable bit called v. So, what will test and set do? It will go and test if v equal to 0, right, if v equal to 0 then make v equal to 1 and return 1. Okay. Else return 0. This is the instruction. Okay. So, let me see, there is a bit v, if it is 0 and I execute test and set, what will happen? It will make it 1 and return 1. If this v is actually already 1, when I do test and set, it will return 0. Okay. Okay. So, what should I do here at this point? Okay. While test and set of v is equal to 0, do. Okay. While test and set of v is equal to 0, do. Oh, anyway, okay, while test and set of v equal to 0, do, right, then I will enter here, then I will make v equal to, I will make v equal to 0 before this point, okay. And similarly here the same thing, while test and set of v is equal to 0, do, and I will again make v equal to 0. And this test and set of v is an atomic instruction. That means when it starts executing, no other instruction can stop it or no other instruction can execute till it finishes, and this is ensured by hardware, right, it will be ensured by hardware. So, initially that variable v will be 0, okay. Now I come here, let producer come and start executing test and set v, it will find v is 0, so essentially it will get 1. The moment it sets to 1, right, when the consumer comes to this point, he will be doing test and set v, and since v is 1, he will be returning back 0, test and set will be returning back 0. So, the consumer will be rotating in this loop, okay. Till when will he be rotating in this loop? Till this fellow finishes count equal to count plus 1 and he makes v equal to 0. You are getting this? So, initially v is 0 to start with, producer starts executing, he comes to this point while test and set v equal to 0. What will test and set v do? If it finds v equal to 0, then it will make V as 1 and it will return 1. So, this will cross this while loop and it will start now making count equal to count plus 1. While it is trying to do count equal to count plus 1, let us assume that this consumer wants to enter, he will come to test and set V, V is already 1. So, every time he executes test and set V, he will be getting only 0, because if V is not 0, I will return 0, if V equal to 1, I will be returning 0 here, please understand. So, I will be getting 0 always, so I will be rotating on this while loop, right. And till when will I be rotating on this while loop? Till this V actually becomes 0. Only when V becomes 0, I will get test and set as 1, I will set it as 1. So, it will be rotating. So, this fellow cannot go and cross this point till this count equal to count plus 1 is completed and this fellow makes V as 0. Once this fellow makes V as 0, then he will do test and set V, right, test and set V is 0. So, he will make, so this fellow will make V as 0, now this fellow will make V equal to 1 and then he will now start doing count equal to count minus 1. By the time he enters count equal to count minus 1, this fellow would have finished count equal to count plus 1. Now, when he is doing count equal to count minus 1, what is the value of V? 1, correct? The value of V is 1 because test and set will make 1. So, V is 1, right. Now, when this fellow is making count equal to count minus 1, the producer cannot enter here because he will come and look at while test and set V, and since V is 1, this fellow will repeatedly be returning 0. So, he will be rotating on this while loop. And when can he enter? When this fellow finishes count equal to count minus 1 and then makes V equal to 0. Then what will happen? V becomes 0, this fellow will execute test and set again with V as 0, then he will get 1 and then, right. So, at the same point of time, both count equal to count plus 1 and count equal to count minus 1 cannot execute in concurrently. When producer is executing count equal to count plus 1, your consumer should be away from this loop, it should be somewhere else in this loop, not at the count equal to count minus 1, it cannot be. And when this fellow is executing count equal to count minus 1, the producer cannot be within this 2 orange spots, it can be anywhere in the loop but not in that spot. By that I ensure that both of them do not execute the critical section at the same time, right. The reason that this fellow and this fellow can succeed this while loop is not possible because test and set is a atomic instruction. If test and set starts executing, it will finish, then only the next instruction cannot be interrupted, like your count equal to count plus 1, correct. So, that is the reason, that's why that's why the hardware need to implement it in an atomic way, meaning one cycle it should finish execution. You are getting this? So, atomic instructions form a major part of process synchronization or any synchronization that we will be doing at the operating system level. So, it is very important that you understand this instruction, right. We will have, so there is another like test and set, there is another atomic instruction called swap A comma B, which can exchange the value of A with B in one cycle atomically. The same thing, here V is exchanged with 0 and 1, there you can exchange it. So, swap can also be used for synchronization, right. You can easily think of a way by which you can substitute swap instead of test and set, right. Okay. So, this is very, very important. So, if you go to the Intel manual, you will see swap or exchange EXCG, I think EXCG or something, okay, exchange or swap, and then EXCHG, I think, something like that, okay, one thing, and test and set, okay, right. So, these are atomic instructions for synchronization, and this forms the crucial part of your operating systems implementation. Thank you very much.